From the spacious studios of Way Happy, this is Mr. Meyer, and we are talking exponential functions. So let's talk about what an exponential. We've been talking about exponentials. Now, anything that has x as a variable, well, let's talk about, x as an exponent. Let's talk about what happens when you graph them. So let's start off with the most simple of all exponential functions, and that would be 2 to the x. Now, when I graph 2 to the x, the nice thing there is that I am graphing something that I can make a table of values, right? I can sit here and I can go x and y, and I can say, all right, if we're going to do 2 to the x here, just to remind me what it is, if I say x is 0, then 2 to the 0 is 1. And if I do x is 1, then 2 to the 1 is 2. If I do 2, then I get 4. I can also do things like maybe a half power. No, I don't know if I could do a half power. Maybe I better go negative powers. Negative 1, that would be 1 over 2, so that'd be a half. There's whatever my half was coming in. And maybe negative 2, I would get 2 to the negative 2. That'd be a fourth, right? So notice I could plot all those points. Well, the reason I was thinking about the half powers, what does that represent? That represents 2 to the half, which is the square root of 2, as we know. And so if I did the half power, that means x is a half. That'd come up here. What y value does that give me? Looks like something between 1 and 2, so maybe like 1.5 or something like that. So you can see if you can graph something, then maybe it makes it a little easier to do some trickier problems. So let's talk about the graphs. The exponential function graphs in general. Here's the formula form. Again, if you've done algebra or pre-calc or anything like that, we wrote it more like this, right? A b to the x minus c. We used h and k, but I'm going to go ahead and use these IB letters. But notice there's your base. And your base has to be positive, and it can't be 1 because otherwise it would just be a line. And A can't be 0 because that would really ruin a lot of things. But B controls how steep the graph is. C controls the horizontal, the left and right shift. D controls the vertical translation up and down. And then just some things that happen with the graph, right? If your B value is bigger than 1, you get a growth graph. Unless it's negative out front, then it's a growth graph in the negative way. So this is if you were getting this graph right here is kind of the most common, what I would call growth graph, because it looks like it's growing. Then you'd have this one is a negative growth graph. Just means it was a growth graph, or growing, getting bigger, growing away from the asymptote as you move left to right. But it was doing it in a negative direction. And then you have what we call decay graphs, ones that get smaller and smaller as you move left to right. Moving towards this horizontal asymptote that they do have. And by the way, that might be something you notice up in this graph up here. Would this have ever gotten to 0? Like if I would have kept picking negative numbers here, like negative 3 and negative 100 and negative 1,000, right? That would be just 1 over 2 to the 1,000. Would that ever get to 0? Not really, but it would get really close, right? I mean, this is a huge number, the denominator right here. And if you only got 1 out of that huge number, you would not have gotten a lot. So it's not 0, but it's darn close to 0, like your chances in winning lottery. So when we sketch these things, there are some things we can talk about. We can talk about that horizontal asymptote, which is easily found if you look up at the blue box. Anything that's added to the back, there's going to be your horizontal asymptote, right? It said right here, D controls the vertical translation, and really what that controls is the asymptote. You can find the y-intercept. Remember, y-intercept is easy. You just make x equals 0. This is D, so I'll just put a little d here to remind us. And then plot 2 other points, and you could get a pretty good sketch. So if they ask me in this problem here to sketch the graph of this function, I could do just those steps. So first thing is I would notice there is a horizontal asymptote at what? Well, that value is negative 3, so that would be x equals negative 3. So here's my graph paper, right? My graph paper like this, and I could go to negative 3. Why would I say x equals? Geez Louise, y equals, oh great, gonna hear about that tomorrow, right? Y equals negative 3, there's my asymptote, right? That is y equals negative 3, this is x, and this is y. And that's my asymptote. Then let's find out the y-intercept. So the y-int is when x is 0, or you can evaluate y when x is 0. So what would you get? You would get 2 to the negative 0 minus 3, Well, anything to the 0 power is 1 minus 3. So therefore, that is negative 2. And that would be right here. And so that is our y-intercept. And then last but not least, let's plot some other points. Let's say x equals 2. So if I do that, if I figure out when y is 2, I would get, not when y is 2, I should say, when y is evaluated with the 2 in it, 2 to the negative 2 minus 3, which is what? 1 over 4 minus 3. What the heck is 1/4 minus 3? Is that negative 2 and 3/4? So negative 2 and 3/4. So what did I plug in? I plugged in x was 2, and I would get negative 2 and 3/4, so almost negative 3. And oh, it didn't work. And there's another point I could plug in when x is negative 2. I could get 2 to the negative, so 2 to the 2 minus 3. I would get 4 minus 3, which is 1. So when x is negative 2, y is 1. So when x is negative 2, y is 1. And you kind of get an idea. If you know these are growth or decay graphs, that definitely looks like a decay graph. And I can definitely draw it like this, right? And that's what my graph would look like. And that's how you can sketch these graphs. So kind of the trick is, know how to do the horizontal asymptote, know how to find the y-intercept, and then just get me 2 other points. It doesn't have to be 2 and negative 2. I just chose them because they were in my notes. But you could have picked 1 or negative 1 or anything like that. And that is how I would graph any of these graphs that are exponential functions. All right, let me ask you a question, and I'll be right back. All right, nice work on those ones. Now let's talk about the practical applications of these beautiful beasts, right? One of them being growth and decay, which you've heard me slip in the words already. So populations of animals and people and bacteria, they just usually grow in an exponential way, where radioactive substances and depreciation of your house or car or whatever usually decay exponentially. And so again, when I think of growth, I think of a graph that is growing from left to right, right? It's growing away from its asymptote. When I think of decay, I think of the exact opposite, something that started far away from its asymptote and came down and is slowly decaying down to nothing. So that is the difference between a growth and a decay graph. All right, so here you go. You have an entomologist, who is somebody who studies insects, is monitoring grasshopper plague and notices an area affected by the grasshoppers is given by this formula, 1,000 times 2 to the 0.2 n hectares, 100 meters by 100 meters, thanks, Abby, 10,000 square meters, where n is the number of weeks since the initial observation. Right, so every week, this is how this thing is apparently either growing or decaying for us. So we're going to find out what it is. Well, the way I would find that out is I could find out the original area. So part A says, hey, how much is affected originally? Well, that is when n is equal to 0. So I'm going to go ahead and put that into my calculator. That's going to be 1,000 times 2 to the 0.2. So if I kind of do the math there, I have the acreage is equal to 1,000 times 2 to the 0 power, or 1. So that looks to me like 1,000. So the original affected area is 1,000 acres, or hectares. All right, and now on to B. Now if I'm going to do B here, I'm going to say, what is the affected area after 5 weeks? So I could plug a 5 in, right? I don't think that would be too bad. I was about to fire up the calculator, but I don't think that would be too bad because it would be 2 and then 0.2 times 5. Isn't that just 1? So don't I get 2,000 hectares? There you go, hectares. And then I, or 2, I think I might actually have to use my calculator now. What was it? It was 1,000 times 2 to the 0.2, and we are doing 10. That's 4, right? Not bad. A to the n, I guess I should say a to the 4 would be probably better notation. A to the 4 is 4,000. How did I do that so quickly in my head? 10 is just going to be 2. 2 squared is 4, right? Now probably the most difficult, 12 a to the 12. Why did, okay, just had people come in and ask me questions. Now my brain is fried. Anyway, a to the 10, this would be a to the 5. This I should have done as a to the 0. Okay, a to the 12, then I would go ahead, if I want to go ahead and do it a to the 12, a sub 12, I would get 1,000 times 2 to the 0.2 times 12, or 1,000 times 2, what is that, 2.4? So I might want a calculator for that. 2 to the 2.4, so 2 to the 2.4 is that, times 1,000, which you probably already were saying is 1,000, 5,200, what was it, 5278. So let's go 5278. And there we go. Part C says draw the graph. All right, I can draw a graph of that, right? Here is my data. And the initial value was 1,000. Let's see, how high did this get? It got all the way to 5,000. So 2,000, 3,000, 4,000, 5,000, right? And I could go out, let's say 5. That's probably not going to be good, but this is a good sketch, or a sketch, I could say. I can just use these points, correct? The first one was 1,000. Then we figured out that 5 was 2,000. And then we figured out that 10 was 4,000. And then we figured out that 12 was up here past 5,000. So I can start to get a good idea of what this graph would look like as a growth graph. All right, let me ask you a quick question, and I will be right back. All right, keep up the good work. All right, now look, you got a diesel generator that gets turned off, and the current slowly dies out of there as time goes on, right? So as time goes on, slowly the generator loses some of its current, and that's all right. So that's what we expect. So there's the formula for it, as you see, and in part A, they ask you when t is 0, can you evaluate the current? So at I of 0, I'm going to try to be a little better at this today. 24 times a quarter to the 0, which is 24 amps, right? And then they say, can you do it for 1? And I say, sure. 24 times 1/4 to the 1 is 6 amps. And that was 1 second later. 2 seconds later, then you would have 24 times 1/4 squared, which would be 1/16th, and that would be 24/16 amps. I guess I could pretty that up. What is that? 12/8, which is that 3 halves? 3 halves, I believe, amps. So you can see that this thing is slowly getting down, 1.5 amps. And I evaluated 3 seconds later, 24 times 1/4 cubed. 4 cubed is like, I don't know, what is that, 64? So that's 24/64 amps, right? Or not a lot. If I had a calculator, I would type it in. Part B says, what was the when it was instantly turned off? Well, that was at I0, so that was 24 amps. So that's how much it's had when I shut the power off on the generator. Part C says, will you plot this for us? And you say, of course I will. I will use the data we had. So we had 0, 1, 2, 3 seconds, I believe. And I had about 24 amps. I don't know, where you want to go? 5, 10, 15, 20, 25. Oh, that's a good graph. Right? And so if I want to go ahead and try this now, I will say the first one was at 24. So 5, 10, 15, 20, 24 was right there. I'm going to use an X this time. And then at 1 second, it was down to 6 already. And then down at 2 seconds, it was down at 1.5. And then it was really tiny down here at 3 seconds. You can see this decay graph. Oh, that was nice. That was a really nice drawing. And why we should probably use graph paper. Right? Remind me to use graph paper. All right. Aside from that, the question is, use it or technology to find out when it's going to reach 4 amps. Well, 4 amps would be right here. And that looks like it's right here. And I'll show you using the calculator tomorrow. Have a day. Stay happy. I still had 3 seconds.